Hi friends, welcome back to Edupedia World. In our previous lecture we saw certain numericals. Today we will focus on conservation of energy. We will see what conservation of energy means. Then we will see conservation of mechanical energy and the condition under which that happens. We will see the verification of the conservation of mechanical energy, and we will see the graphical representation of conservation of mechanical energy. Let us get started with today's lecture. The law of conservation of energy. This states that the total energy of the universe remains constant. Total energy of the universe remains constant. That is, that energy can neither be created nor destroyed. It can only change form from one kind of energy to another. Energy can neither be created nor destroyed. It can only change form. It can be transformed from one kind to another, one kind of energy to another kind of energy. So the law of conservation of energy basically implies that the total energy in our universe is bound to remain constant. Energy will not be destroyed, nor can it be created. Implication of the law of conservation of energy when we confine our study to mechanical energy is that if there is no frictional losses, then the total mechanical energy remains constant. So conservation of mechanical energy states that the total mechanical energy, that is kinetic energy plus potential energy of a body remains constant. And when does this happen? This happens when there are no frictional losses. When no frictional losses takes place. In this chapter we will be dealing mainly with the conservation of mechanical energy. So we know that a statement of conservation of mechanical energy is that sum total of kinetic and potential energy remains constant. Now let us prove it mathematically that in fact the total sum of kinetic and potential energy remains constant. In order to prove this, we will take the example of a ball dropped from a height h. Let this be the surface of Earth. Let a ball be at a height h. So the initial height is h. We assume that the potential energy at the surface is 0. This is the reference we define, and with respect to this we'll find the potential energy at other positions. Now we know that the potential energy at a height h is given by mgh, where m is the mass of the body. So this ball has a mass m. Therefore I can write the potential energy is mgh at this particular height, and the ball is dropped from this location. So we can safely say that the velocity here is u is equal to 0. That is, the ball is initially at rest, which implies that the kinetic energy at the highest point is 0. Now we have seen the highest point potential energy as mgh and kinetic energy as 0. Let us take an intermediate position. Let's say this as the position, and this position is at a distance x from the position where it is dropped. So the ball has traveled the distance x to reach this particular position. This is an intermediate position where x is less than the initial height, that is x is less than h, so that this position is anywhere between initial ball position and the surface of Earth. Now if we want to find the potential energy at this position, we need to calculate this height, because the potential energy at this height will be given by mass into gravity into the height above the surface of Earth. Now we can see that this height is h minus x. So I can write it as h minus x. Now since this is h minus x, this height, the potential energy at this height is equal to mg times h minus x. Now next I need to find the kinetic energy at this position. In order to find the kinetic energy at this position, I need the velocity at this position. Let me assume that the velocity at this position is v1. Now I will use the equation of motion to calculate what is the velocity. How can we do that? This initial position, the velocity u was 0, and from here to here the distance traveled s is equal to x, and the gravity, the acceleration acting is downward with a magnitude g. Now we will use the equation of motion. What do we know about the equations of motion? V is equal to u plus at, s is equal to ut plus half at square, and v square minus u square is equal to 2as. So here in the third equation we know the v, rather we need to find the v. We know u, we know a as g, and we know the distance covered as x. So I'm going to use this equation. V square is minus 0 square is equal to 2 times g times x. This gives me v square is equal to 2gx. And we know that kinetic energy is equal to half mv square, which implies that the kinetic energy is half times m times 2gx, and that is equal to mgx. So the kinetic energy at this intermediate position is equal to mgx. Now if we sum up this potential and kinetic energy, we see that the sum is mgh minus mgx plus mgx. That gives us mgh. This is the sum of potential and kinetic energy. Similarly, at the highest position, the sum was mgh plus 0, that was mgh. So this is the column of mechanical energy, the total mechanical energy. At the highest point it was mgh. At an intermediate point it is mgh as we calculated. Now let us see what is the value at the lowest point, that is at the surface. In order to calculate that, we again need to find the velocity here so that we can calculate the kinetic energy at the surface. We will use the same expression, same equation, v square minus u square is equal to 2as, but now the s will be the total height h, since the ball has traveled the height h to reach the bottom. Let us do it. Let us imagine that the velocity here is v. In fact, this had to be v1 since we have assumed it as v1. but here the velocity is v, so it will be v square minus again the initial position, that is the top position, the velocity was 0. So again it is 0 square is equal to 2 times a is gravity g and s is the total height h, since h is the total distance traveled to reach the bottom. This gives us v square is equal to 2gh. Now kinetic energy at bottom will be half times mv square, that is half times m into 2gh. 2 cancel, we get 2gh. So this is the kinetic energy at the surface of Earth. Kinetic energy is equal to mgh. Potential energy over here is 0 assumed as the reference. So if we add these two terminologies, the potential energy and the kinetic energy, the total mechanical energy adds up to mgh again. So through this example of a ball dropped from a height h, we see that the total mechanical energy remains constant, remains the same at any point during the trajectory of its fall. From this we can safely say that if there is no friction present, then the total mechanical energy of a freely falling body will remain constant. That is, the conservation of mechanical energy is upheld here. There has to be no frictional losses. If there were a air resistance, then the ball would lose velocity and the kinetic energy would be lower at the bottom than mgh, and the total mechanical energy would fall then. But since there is no frictional losses, the total mechanical energy at any point remains conserved. So this is an extension of the conservation of energy, and this is what we will mainly deal with in this chapter. So we'll focus on this. Now let us try to plot this whole phenomena and graphically represent what is happening here. The plot for the energy versus the distance from the ground for the falling ball can be shown like this. If this is distance above the ground, distance above ground, and this is the energy axis, then as we have seen that the total energy, that is the total mechanical energy, will remain constant throughout. And how much will that be? That will be equal to m times g times h. This is the total mechanical energy. Now since this is the distance from above the ground, so this point is the ground level, and as we have seen, at the ground level the potential energy was 0, and as we increase the height the potential energy increases, and it was a linear relation. So basically a straight line. This is my potential energy plot. Potential energy. What about the kinetic energy? In the kinetic energy, the highest point, at the highest point the ball was stationary, so there was no kinetic energy, and the kinetic energy of the ball, or the velocity of the ball, increased as it reached the ground. So now this will be again a linear plot, but of the opposite nature. That is, as the potential energy is increasing, the kinetic energy is decreasing, and the kinetic energy is maximum at the surface and minimum at the highest point. Potential energy is maximum at the highest point, minimum at the surface, and the total mechanical energy, that is the sum of kinetic and potential energy, remains constant throughout the process. This is exactly what we had seen mathematically. Now at this point, the potential energy and the kinetic energy will be exactly equal, and they will be equal to mgh by 2. Now the only way to increase the total mechanical energy is to drop the ball from a higher point. If we increase the height h, then the total mechanical energy increases. Also, we can find out what is the maximum velocity of the ball when it reaches the surface. How can we do that? We can do that because we know that the maximum energy is mgh. That is, the total mechanical energy maximum is mgh. And we also know that the kinetic energy is given by half mv square. So for the lowest point, where there is zero potential energy, the whole total mechanical energy is due to the kinetic energy. Therefore, the maximum velocity will be at that point, and that can be calculated using this relation, which will give me v is equal to root under 2gh. So my maximum velocity, this is the maximum velocity. Maximum velocity is root under 2gh at the lowest point, that is at the ground level. Now with this we have seen the whole conservation of mechanical energy phenomena. In the next lecture we will see an example where the conservation of mechanical energy takes place, a simple example, which is a simple pendulum. And then we will read about degradation of energy. The degradation of energy is that dealing with frictional losses. As I have said that here there is no frictional losses, but in real scenarios there can be frictional losses which leads to degradation of energy. We'll see those two in the next lecture. So till our next lecture, have a great day. Goodbye.